자, 그러면 let's start the third PowerPoint file I have posted. So this is about the solving Schrödinger 2D Schrödinger equation. Using the 2D del scale operator we have just introduced. Right, so this is an example when the potential, two-dimensional potential is given like this. If x is less than 3 nanometer, the potential is 0.1 electron volt, minus 0.1 electron volt. And when y is less than 2 nanometer, it is like this, and otherwise it is the 0 electron volt. Then the Schrödinger equation is given like this. This is del operator. Del square is given like this. And we can convert this to the sample data point. The del operator for the two-dimensional sample data point becomes like this. These are 4 neighboring data points minus 4 times the data points at the center. So this is a 5-point representation of two-dimensional del square. For one-dimensional del square, we represent this with 3 points, right? 2 neighboring point minus 2 times center data point. Right? So as it becomes three-dimensional, it becomes 5-point rule. And if we extend this to three-dimensional, how many data points do you need to represent del square? 7. Right, that's correct. 7-point rule can be applied for two-dimensional del square for a given three-dimensional potential. Right? But this one should be V as a function of x and y, and psi also function of x and y. So V is given like the potential at a given point times the psi at a given point, and E is the constant, and this is a psi at a given point. So we just represent this for a given boundary like this. If we have consider minus 8 to 8 along the x-axis and minus 6 to 6 along the y-axis, and this is the potential given. If the x is from minus 3 to 3 and y is from minus 2 to 2, potential is minus 0.1 electron volt. Otherwise, it is 0 electron volt. And we just take the 80 data points along the x-axis and 60 data points along the y-axis. That means 0.2 is the interval between the neighboring data points. And we just combined three-dimensional data points from here. This is the beginning, and this is along the x-axis. We have 80 data points and another 80 data points, and so on. So we add these things. We have 80 data points first row from the bottom. We have 80 data points, and we just combine 80 data points. And these are the second row from left to right. So this is the second data point, and so on. So we have combined all of these data points, and potential is also sorted like this. V1 is potential over here, and V80 is the potential over here. 381 is the potential over here, and 82, and this is 160, and 161, and so on, like this. So we have 80 by 80 data points for the del square operator. And we have diagonal component 1 and 1 and another 80 points. And the other one, they are all zero matrices like this. Other one is 0. And we have first 80 by 80, it is -4 at the diagonal direction, and 1, and another one at the off diagonal component. And the second block, it has identical matrix like this, and at the center we have this the same matrix is at the center. So these are the representation of. Oh, I think I omitted one page to describe this. Let's see. Why it is like this? There is one page missing. Let's see, how can I do? Right. At this moment, let's accept these del square is given like this. I'll add one more page why del square is given like this. So you can just assume this is correct, and I'll explain after that. Just a moment. Then this is the two-dimensional plot for a potential from -6 to 6. From -8 to 8, we have a potential, well, two-dimensional potential given like this. And then we can just solve the equation, and this is the eigenvalue, first eigenvalue and the first eigenfunction correspond data points of the eigenfunction, and this is the shape of the eigenfunction, and this is the second eigenstate energy, and it's the probability density function, and this is another the pseudo color representation of this one. The same thing, and this is third one. It looks like this one, but its orientation such that this is along the y-axis. Here, this is along the x-axis. Right? This is along the y-axis. So we have the potential well is from -3 to 3 along the x-axis, from -2 to 2 along the y-axis. So if it oscillates along the y-axis, it has higher eigenvalue. So it is the third eigenstate. And the fourth one looks like this. This is along the x-axis. So along the x-axis, this is the oscillates along the x-axis, and this is eigenvalue. And this is another, the fifth eigenstate, and this one looks like this. And so there exists the fifth. So this should be E5 instead of E4. So there exists 5 energy state and corresponding 5 eigenstate solutions. And these are the MATLAB code. As before, this is the only statement. Psi and energy is eigenvalue and eigenfunctions, eigenvectors of A, and these are just to form a matrix A. And the rest of them is to find which one is a physically meaningful solution. So only eigenvalue, eigenenergy, if it is less than 0 electron volt, is the physically meaningful eigen solution, and there exist 5 of them. So that's here is a homework number 9. It is not posted yet, but I'll post this, and you'll find the solution of this equation. Right, let's go back to the, I think I didn't post it that here, so I'll, let's say, right, this is not posted yet. I should find out which file is missing. Let's see. Maybe it's over here. No, this is just. These are just. This is a bit similar representation. It is this, but it is a little bit different because this is an electrostatic Laplace equation instead of Schrödinger equation. So I cannot use this one. Let's see. Let's see whether what can I do? I can find the file over here. Let's see. First of all, do you have any question up to this point about the two-dimensional, except for the page to explaining about the why it is given like, why del square is given like this. I need another page, and I'll explain it later. Except that, do you have any question up to this point? 자, 그러면 okay. Allow me about 5 minutes to find out correct file, and I'll post it this morning. Oh, okay, internet is connected, so I can post it right now then. Okay, here it is. I found it, and I'll post it right now. Just a moment. Okay, I've just posted it, and that file will explain why or how how to find the right. 2D differentiation matrix. We have just explained this, a 5-point rule. And these are the examples by taking 5 data points along the x-axis and 4 data points along the y-axis. So we have psi 1 from here to here, and we assign psi 6 over here to 10, and 15 from 16 to 12. So we have grid size 4 by 5. So along the y-axis we have 4 points. Along the y-axis we have 5 points. And as there exists 20 data points, the eigenvector, or each sampled data point, is from 1 to 20. And as I mentioned, in order to calculate the 2D del scale operation at given psi 1, we need to find the left side value and the lower side value as well. And we do not know these values. And these values are not included within the sample data point either. But in order to calculate del scale, we should just assume this value is same as the neighboring point. And this value is same as its neighboring point. And this one is also unknown. We assume this one is equal to its neighboring point. And at the top, we also assume this point is equal to its neighboring data. So for the first 내가 아까 문을 열어놔가지고 더 시끄럽네. 문을 열어놔가지고. 훨씬 낫네. 고마워요. 자, 이번에 에어컨이 없어서 위에 있구나. 그냥 합시다. 자, 봐요. So, for this point, del square is just psi 1 plus psi 1 plus psi 2 plus psi 6 minus 4 times psi 1. So these value 2 of this and 2 of this cancels out, so we have just minus 2 psi 1, psi 2, psi 6. And this value also is represented like this. And 7, for example, 7 is a regular 5-point data point, because for the data point 7, the every other values, neighboring values are known, so we have just this representation. Right. So if we keep writing this like this, psi 1, 1, that's this point, besides, and 1, 2, 1, 3, and 1, 5. And 1, 6, 1, 7, and so on. Then it is like this. So h square times psi 1 double prime is minus 2 psi 1, psi 2, and 0, 0, and psi 6. Can you see that psi 1 h square times psi 1, right, is minus 2 psi 1 plus psi 2 plus psi 6. So this psi 6 one is represented in matrix as 0, 0 times psi 6. And the second data point is given like this, and there is psi 7 as well, and rest of them is 0. So these are the matrix representation for 20 by 20 matrix. So if I represent this with del square times right side psi 1 to psi 20, this is the matrix. So each one, this is 20 by 20 matrix, and there exists 5 by 5 block, 5 by 5, 5 by 5, 5 by 5, and 5 by 5. And there are 4 of them because along the y-axis, there are 4 data points. Along the x-axis, there are 5 data points, so it becomes 5 by 5. If I go back, here, along the x-axis, we have 5 data points. Along the y-axis, we have 4 data points. So the whole dimension of psi is 20 by 20, right? So 20 by 20 matrix. We have 20 by 20 matrix, but it consists of 5 by 5, another 5 by 5, 5 by 5, and 5 by 5. So 4 of them, because there exist four rows along the y-axis and 5 columns along the x-axis. So that defines 5 by 5 matrix, and it becomes minus 3. And this one is a little bit different, but these are all the same. The rest of them, these are all same, and this one is same as this, and this is off diagonal point, and this is identical matrix. The rest of the matrix elements are all 0, and these are all zeros. So we need to define this one. Right. So if we have n by n element, so we have n element along the x-axis, m element along the y-axis, we can either, right, previously we assumed its neighboring points are identical to itself, right? And that makes a little bit complicated matrix like this. And if we assume the neighboring points are all 0, for the electromagnetic Laplace equation, this will produce different result. But for Schrödinger equation, this will produce same result. So this is the another boundary condition I have explained. One is Neumann boundary condition. The other one is Dirichlet boundary condition. And this is one of them. I cannot remember which one is which one, but this is simpler representation. If we assume this is 0, then this one becomes like this. This is simpler. And if we represent that with the 20 by 20 matrix, it becomes like this. So these one all looks identical. Minus 4, 1, 1, minus 4, and so on. So this is the choice we are going to use. And for n by n matrix, we have this. So for n by n, right? So n is the number of elements along the x-axis. M is the number of elements along the y-axis. So if we take 100 by 200, then this one becomes 200 by 200 matrix. And if M is 100, we have 100 of them along this direction and this direction. That's it.
Just 여기서 저희가 이제 매트릭스에 대한 걸 구했잖아요. 좀 정확해. 이거를 쓰는데 그러면 굳이 이거를 이렇게 표현할 이유가 있나요? 지금 그러니까 H바의 H바 P사이 해가지고 이제 제가 나열했잖아요. 그 매트릭스 합을. 근데 제가 전에 이 앞에 있던 식에서 사실은 제가 썼던 이유가 이제 그 P사이별로 값을 그래서 뭐 차이들을 쓴 거잖아요. 3.5 이용해가지고. 근데 여기서 이거를 거기 순수들을 이렇게 나열해서 매트릭스처럼 만들었을 때 나온 이점이 따로 있나요?
그 매트릭스로 만들어야지 아이겐밸류를 우리가 솔루션을 구하지. 원래 오리지널 이퀘이션이 슈레딩거 이퀘이션이 아이겐밸류 이퀘이션이죠. 그래서
그 지금
어디 갔지?
어디 아이겐 스테이트 P사이를 구할 수 있다는 저희가 그 가장 큰 거니까.
그렇지. 디퍼런셜 이퀘이션 푸는 과정입니다. 이게 자체가
그럼 그래서 이게 원래 그 P사이도 뭔지 정확히 이게 좀 아이겐밸류 모르는 상황인 거네요.
그렇죠. 모르는 상황이죠. 이거를 지금 푸는 거예요. 요거를 이게 P사이 x, y인데 내가 이게 요거 뭐 델 스퀘어만 2디멘션으로 썼는데 요 디퍼런셜 이퀘이션 푸는 과정인데 어떻게 하느냐? 2디멘셔널 그리드를 만들어서 샘플링 포인트를 가정을 한 거죠.
그럼
그 샘플링 포인트가 만약에 x축으로 100 데이터 포인트, y축으로 뭐 300 데이터 포인트를 했다 그러면 200 곱하기 300 그러면 6만? 6만이죠. 60,000 data metrics, data points. So, like the case for the one-dimensional differential equation, right now we have the eigenvalue equation, eigenfunction, right. Schrödinger equation is itself del square plus 3 x and y is x and y. So this is a two-dimensional operator, and this one can be matrix. Right? Multiplied with the column vector is equal to E times column vector. So matrix product with the column vector equals a constant times the column vector. This is a typical M times matrix A is equal to E times matrix A, the vector. So this is a typical eigenvector equation, eigenvalue equation for matrix, and this one becomes n by n. Sorry, A is m by n. The size of A is n by n, and m by n is the space, two-dimensional space we are going to represent for a two-dimensional function psi. The mission is what is this is mission. What is the psi x and y? Which satisfy this differential equation for a given potential Vxy. So here, the potential is only small at the rectangular shape at the center, and the other area potential is 0. Then what will be the solution? And solution, we assume the sample data point from left to right. So let's say this is n is 200 data points. Along the y-axis, we take m is equal to 300 data points. Then how many total sample data points there exist? we have psi 1 to psi 600. Sorry, 60,000. Right. So we have 60,000 data points from here all the way to the final, the end point. So this is psi 1, and this is psi 60,000. Right. And these data points satisfy the eigenvector solution. This is given by using this matrix and this given potential, and we define this one, and then the eigenvalue and eigenvector corresponding to the eigenvalue is the solution to satisfy this eigenvector equation. So these are the situation we have. So this is just a natural expansion of one-dimensional Schrödinger equation to two-dimensional Schrödinger equation.
선생님 서 매트릭스로 나누는 이유는 그 어떤 건가요?
서 매트릭스로 나오는 이유는 여기서부터 그냥 요걸 이렇게 하기 때문에. 그래서 왜 그러냐면 여기 이 포인트에서의 그 델 스퀘어는 여기 더하기 요거 더하기 요거 더하기 4배 요거잖아요. 그죠? 그러니까 요 데이터 포인트가 있어야 되는 거죠. 그러면은 이걸 어떻게 되느냐? 얘가 지금 요 포인트하고 요 포인트는 요 매트릭스 상에서 아까 질문 시간이니까 가도 됩니다. 수업 있는 사람 가도 됩니다.